at Purdue. And today we're going to talk about space elevators. So I'm going to share a PowerPoint with you. Let me bring that up. Of course, that's not where I wanted to start. So let's go back to the beginning. So elevators to space has been in the works for, I don't know, about 10 years. Um, when I left the classroom to come to Purdue in 2006, um, I worked for a nano project, and one of the charges that we were given was to develop learning instructional materials for middle and high school teachers utilizing concepts in nanoscience. And so that's where this came from. And that's the connection between elevators to space, grand scale things, and carbon nanotubes, nanoscale things. So we'll get to a little more about that in a little bit. But when you looked at the lesson and listened to my video, you found out that there were ideas relating to getting to space by an elevator or some kind of a structure going back 100 years. This gained impetus in the 1960s with NASA as well as other countries taking the idea a little more seriously and actually proposing some designs. The constraint, however, was having the right materials, not only for the ribbon, but for other components. And so it kind of sat dormant until the 1990s, until the discovery of carbon nanotubes, and the whole idea took off again. So if you do a little Googling, you're going to find some crazy stuff out there. So I've got a couple of resources here. The L5 Society, started by a few people, primarily Eric Drexler and Timothy Leary. These guys are futurists. I mean, this goes back probably, I don't know, 15 years. And I'll just say it. Okay, they're a little kooky, but they had some interesting ideas. Anyway, the L5, it refers, L is the Lagrange point. So if you have the Earth and let's say we are the Earth, we have the sun and the moon, there's a point between the sun and the moon where the gravitational attraction between those two things is equal on an object. That could be the Earth or it could be a satellite. And that's called the Lagrange point. And so that's the basis of the L5 Society. In the bottom right is an artist's conception of an environment for living in space. I mean, so I don't need to dwell on this. There's just all kinds of stuff out there to build the hype for maybe why we would have an elevator to space or why it would be a good idea. So potential benefits. By the way, I'll share this PowerPoint with you. It'll be in the folder with the other materials a little later on today. Economy. Rockets are heavy, they're cumbersome, they take time to build, they use a lot of energy. And to put a man in space, a person in space today, is about $1.3 million per person. Predictions are with something like a space elevator that could drop drastically. Rockets have to do a lot of work to overcome gravity. Space elevator would be more of a gradual ascent, and overcoming gravity would take less energy, take more time, but would be more efficient. And I'm not going to read all of these, but out of a project like the space elevator, new innovations. I mean, think back about what the last bullet talks about: disruptive technologies, things that revolutionize the way we do something or what we do. The Apollo mission, robotics, the first uses of electricity. Electricity was a disruptive technology. It was something that set topsy-turvy everything that we thought about light and using energy. And so out of these grand schemes, we get new materials, we get new innovations, and new ideas with creativity. Um, oops. There are also risks and big questions. The cost to do anything like this would be hundreds of billions of dollars. Material science is not ready. We don't have the materials. Some work is being done using carbon nanotubes and other materials to create a composite that would be strong enough maybe to construct the ribbon, but we're not there yet. Um, there are a lot of questions. Can we do it? Should we do it? Should it be a global effort? Should it be cooperation between countries? Would it be competitive? What about things like military targets, hackers, revolutionaries, radical segments of societies? Um, Not only when I say environmental impact, I don't just mean the impact of the environment on having the structure. I mean the impact on the environment um, for making these materials. What's the cost in terms of environmental risk in making these materials, in doing this kind of a project? This is a good brainstorming activity for your students to do a little research and come up with, you have a debate, the risks versus the benefits. So there's a lot of social, political, environmental, ethical debate here. Just because we can do it, should we do it? So the theory is you have the Earth, you have a station in geosynchronous orbit, and you have a counterweight. Um, think about, when we were kids, some of us, you hold a bucket of water and you spin around, and the whatever you have in your hand, it could be a tennis ball on a string. When you turn around, there's a tension on that string, and the tension is by the acceleration of that object in a circle, in a tangent around, in a radius around you, and it's that tension that would cause the cable to be tight enough, keep it taut, and allow the climber or the vehicle to climb up to the space station. So that's pretty much the theory. So you might say, okay, who's working on this? Is this really something that people are taking seriously? Every year since, well, maybe the last 20 years, NASA has had a competition annually to invite people to create a climber, a vehicle, a robot, whatever you want to call it, that would be able to climb a cable and reach a given altitude. And the prize is given to the team who has the most successful climber, the climber that would get to the highest altitude. So NASA takes this seriously, maybe a little tongue in cheek, but they're pursuing options. Japan right now is doing work to create a climber capable of reaching 100 kilometers in altitude. Now that's a fair distance. That's not been done before, but Japan is working on that project along with, well, in competition with China, the EU, and other countries. So, I guess this is not going to be a project where China and Japan will collaborate, and certainly China and the US currently are not going to collaborate. So this would be a competitive thing, and that's probably, it could be good, it could be bad. I guess that's debatable. So maybe there would be one space elevator, maybe there would be more than one. So we talked about carbon nanotubes, and a carbon nanotube is a cylinder of purely carbon. It is a hexagonally shaped, well, the angles between the angles made by the atoms in the nanotube are hexagonally arranged. So think about chicken wire, for example. Chicken wire is hexagons of wire. Think about that shape. Uh, Graphene is a sheet of carbon with the atoms arranged hexagonally. Graphite is basically larger scale graphene. Graphite is larger clumps of molecules. Graphene is a single layer of molecules, one atom thick. Think about a chicken wire wrapped around itself to make a tube. Think about the chicken wire, the wire actually being something really small, like spider silk. A human hair is still many, many, many times larger, like 80,000 times bigger than a carbon nanotube. This is an incredibly small scale. However, so you have a carbon nanotube, which is, if you held it up, it could be 10 or 20 centimeters long. It would be invisible. So if you could pull it, you could feel it, but you couldn't see it. Interesting idea. So carbon nanotubes are one potential material for space elevator materials. So from a carbon nanotube, the constraint we have right now is carbon nanotubes can't be made meters long. They might be approaching that, but how long of a tube would we need? Well, can we take shorter tubes and weave them together or somehow combine them? So can we make nanofibers? Can we make polymers? Can we make composite materials? If we have a matrix in which to embed combined carbon nanotubes, maybe we have the basis for coming up with the right material. So if you have any questions please put your question in and I can address it. I don't see Bill on the screen. I don't know if he's still there or not. Bill, are you still there?
I'm still here, David.
Okay, I don't see you, but maybe.
Because I'm playing hide and seek with you right now. It's kind of fun.
Well, you're probably just checking, I don't know, you're reading comics or something. Anyway, so with all that said, how does this relate to the lesson? Well, we're talking about innovative materials, super strong materials. This is a kind of a lesson in materials, material science. So the fundamental part of this is a tensile test. How strong are materials? So how do you describe materials? They can be hard, they can be brittle, they can be ductile, they can be malleable, they can be plastic, they can be elastic. So these are all terms that we can refer to in talking about strength, stress, and strain. So, I guess I would like to probably have my students think about some examples and talk about things that might be hard, but not very strong. So I might pose that question to you. What might be hard and not very strong? Well, how about glass? Glass is hard, but it breaks pretty easily. It's brittle. And it's not elastic, it's not malleable, and it's not plastic. It doesn't stretch, it doesn't bend appreciably, and it will fracture and fail with a certain amount of pressure. And I look around this room in which I'm sitting and I see cement block walls. Are cement block walls strong? Are they hard? Yes, I think they're hard. Are they strong? I've seen many cars drive through cement block walls in accidents, so they may not be very strong, at least in the sideways direction. They might be stronger in the vertical direction. And so some materials have different strength properties in different dimensions.
David, a question was asked. I can imagine the nanotubes sway with weather or the Earth's rotation. I wonder how scientists would overcome this.
The nanotubes would be part of a larger material. So yeah, I've seen predictions, I've seen theories stated where nanotubes are strong enough to support this kind of a grand project. Um, a, a ribbon this size of carbon nanotubes, so practically as thin as paper, 3 or 4 or 5 centimeters wide, um, would be strong enough to stand the stress of the counterweight out in space. Now, I don't know. I find that a little bit hard to believe, but these are incredibly strong fibers. However, in the end, the carbon nanotube would more than likely be part of a composite of molded with another material. And so I don't think it would be carbon nanotubes alone. I think it would be carbon nanotubes um, as a complement to another material. So here's a stress strain curve. Now, when you think about it, strain is a ratio, excuse me, strain is a ratio of the amount of stretch in a material divided by the original length. And so, I'm thinking about customarily graphing things with, which variable goes where, and stress being the thing that causes the stretch. Stress causes the stretch. Stress is pulling on the spring. Um, it seems like that would be on the x-axis, with the result being on the y-axis. And you're entirely right if you think that. However, material scientists graph it this way. I'm not sure I can tell you why. Well, I can't tell you why, but that's just the way it is. So this graph compares two materials, a brittle material and a ductile material. So the brittle material is the red line, and you see it can initially stand more stress than the ductile material, meaning that it doesn't stretch. It doesn't deform as much as the ductile material. However, it reaches a point where, since it doesn't stretch, it breaks, and so it fails. Whereas the ductile material has a much broader curve. And I have a second slide that I'll show you that is a little more explicit. But you see the ductile material, the flat part across the top is the material stretching. So the initial part, the slope, the kind of straight line of the blue material, it's also stretching, but it will come back. It's not deformed. As it rounds the curve and goes across the top, it is deforming, and it won't come back to the original shape, and it will eventually fail. Let's take a look at another slide. So we're going to compare again brittle and ductile, but what I'm interested in are some of the points on this curve. We see let's look at the green curve for a minute. We see the elastic limit. Well, the elastic limit is on both curves, but it doesn't matter which one we look at. It's where the material deviates from the straight line and begins to begins to just deviate from the straight line. So what happens at that point? At the elastic limit, as the material continues to deform, its deformation is permanent. It doesn't come back. So if you look at the endpoint of both of those, we have the brittle failure and the ductile failure. So at some point, I mean, think about a wire. If you stretch a wire, a thin wire, it'll stretch and it'll eventually break. This is the way they test bolts in industry. When they make a bolt or a screw or a nail, they clamp it in place and stretch it and see how much it can take. Um, in that region, just before it breaks, they call that the plastic region, where it deforms and then ultimately fails. So um, I'm not going to talk about Young's modulus at this grade level. It's just a ratio. In the physics books will use Young's modulus, um, or they'll just call it the modulus. But so I will relate this to some data that I took in this experiment in a short while. Bill, do we have any other questions?
Not right now, David.
Okay. All right. Well, let's move ahead. So I'm going to talk about this experiment. As I mentioned, I started working on this experiment um, about 10 years ago, give or take. And when we did, I developed this experiment for an 8th grade group, actually. And it was part of the Super Saturday program at Purdue. And so I did this with 8th graders. And when we first devised the experiment, we used plastic, the same thing that you used, except we used a hot glue gun. And so we gave the students 2 pieces, and this is actually from 10 years ago. This is the real thing. We gave students 2 pieces of plastic. We gave them a fixed amount of string, a hot glue gun, and some hot glue. And their challenge was to draw a picture, to sketch the outline of the ribbon, and draw a picture of what they would do with their string. So in an engineering design fashion, they had a limited amount of resources. They had glue and they had string. The plastic sheets were cut. And so their challenge was to take the given length of string they had and arrange a pattern. They could cut it, they could not cut it, they could leave it one piece and loop it back and forth. They could do whatever they wanted, but they had to propose a design and defend their design. And um, and that worked okay. In fact, it worked pretty well. But we thought it would be better. It wasn't a really good example of a composite material because we have the plastic, we have the string, and then we threw in the glue. And the glue, the hot glue added another component that was not just um, the plastic and a string held by an adhesive. Now, you could argue that the adhesive that we used, maybe the rubber cement, adds something too, and it might. But the hot glue definitely made this stiffer, and it just didn't seem like a very good model. So we played around with some other ideas. And, we tried spray adhesive, and, we used Elmer's, and there are other spray adhesives. I don't dislike that, but I think you have to be careful doing it in a classroom. And, I did this in my family room and didn't seem to be too bad. So, but I didn't go crazy like 8th graders might. So if you have a safe place to do that, that might be an option. However, the working time on this kind of an adhesive is pretty small. Anyway, so in there was a time in between where we started with the hot glue and where we ended up now, where we really, I think, I'd say hit the jackpot on modeling a composite material using a nanoscale material. So in the true sense of the word, I wanted to create um, a composite that had a true nanoscale component. And so I'm skipping down to the next to the last bullet, polyvinyl alcohol. Um, we, we would call it PVA for short. You can buy PVA from any of the scientific supply companies that you would typically deal with, Flynn and the other companies. I can't think of them because I usually get my stuff from Flynn. PVA is non-toxic. I mean, you wouldn't want to eat it, but it doesn't hurt you. Um, it's a stuff that you dissolve in water, hot water, and it'll cure into a plastic. And so we tried PVA, um, and if you're interested in this, I can send you more materials. I think this is a little more a high school way to do it than a middle school way to do it, uh, but you could. You, in brief, you mix up the PVA. You have you separate it into two batches. So you have, maybe 50 milliliters of each in a cup, plastic cup. You pour one out on a piece of glass or plexiglass, and take a large diameter, like a half-inch diameter threaded rod, and you draw the material down with the threaded rod to smooth it out to a uniform thickness. The second batch, you add another material, and we used nanocellulose, which is a true nanoscale material. You couldn't do this in a school because it's hazardous to breathe. However, I found that I had a source for, now I'd say I had a source. I bought this a few years ago. This is, I don't know how well you can see that. It's fiberglass. It's just little pieces of fiberglass. They're about 3/4 of an inch long, and it's a pain to separate them and pull it apart. However, that could be another option. Not necessarily for doing the PVA, but you could do that with the plastic and rubber cement that we did here. So I didn't try that with this experiment. Honestly, I forgot that I had it until I discovered it getting ready for my presentation today. But that might be another option. In any case, I don't think the PVA option is, number one, you need hot plates. It's a little more involved. I'd, for 8th grade, prefer to keep it simple, but if you want more information, let me know. Doing this experiment, there were a couple of things that I think I should reinforce safety, and that is when your wooden board has, this board has more holes in it because I tried different things, but I would clamp the long end, put the spring on the shorter end, and there is a time when, as you're pulling this is a fair amount of force. If the ribbon fails, then the student pulling is going to end up with one piece, and the spring is going to flip back and go the other way. That's a definite hazard. So don't let any kids stand on the back side of this while the other students are stretching, because it could be harmful.
David, we have one thought.
Yeah.
They also thought about the sway with the rotation and shielding from solar wind, just making all those variables that you're going to have to think about when you're thinking about this elevator going to space.
Oh, okay.
But then the other one was, what materials do you recommend for middle school? How long would you spend on the project? A week of 50-minute classes, question mark. Can I throw my 2 cents in?
Sure.
So I taught middle school for quite a few years, and I actually taught 8th grade. I taught 8th grade the whole time. I taught 7th grade 1 year as well. This to me, when David was explaining all this, I'm thinking this is the end of my 9 weeks project after I've done a bunch of stuff with Newton laws and forces and all this other things, so I can start bringing all those together. And I always did, at least when I did it, we taught a lot of chemistry in the first semester and physics in the second. So this would be awesome, because then we could go back and tie in some chemistry as well, bring that all back in. And I could see this taking a week. Or you could do what a lot of other people do and spend, every Friday for so many Fridays doing it. That way it's kind of, that's the, I'll say, reward for the rest of the week's work, and then spend Friday working on this. The materials, David and I were talking about this quite a bit. I think the materials are like almost kind of never ending. It's what do the kids think? Try to brainstorm, let them test a couple things, and quickly they're going to be like, well, that doesn't work very well at all. And I think sometimes that's better than, giving them the right stuff to use. It's letting them come up with a couple things. Now, you don't want to have them burn too long, and I would think after a while maybe you're going to, you know, narrow them down into what they should actually probably be using better than, I don't know, whatever they come up with. What do you think, David?
Um, I think I agree with, for the first time in a long time, I think I agree with what you say.
That doesn't happen very often, people. So I want you all to be witnesses. I'm glad you're all here, and that I'm recording this session is awesome.
Oh boy, you have me on recording now.
And the other thing that people brought up was like, recycled materials or things like that, that you could maybe bring in as well. Things that might be readily usable. And I think this is also a great time to contact your local hardware store or companies around you to say, hey, here's what I'm doing. I'm looking for some supplies that might be able to be used with this. Would you guys be willing to even, give me that and give me the specs that go along with it so that I can, maybe the kids can choose from it. So there you
go. Bill is right. We brainstormed a little bit, and I'll come back to that. But as far as the timeline goes, on page 5 in the teacher materials, I give a 4-day plan for this this experiment. I think it's flexible. I could probably do 8 days with this, with social issues and weighing the ethics and so forth. But I think 4 days is probably reasonable, as probably a minimum. But if you're short on time, you can pare it down to whatever suits you. As far as materials go, Bill and I, because I kind of ran out of ideas. I had tried some things. I threw it out to Bill, and he gave me some ideas. One of the things Bill thought of was a Kleenex, like a facial tissue. And so I tried that, and I think that's a pretty unique idea because Kleenex isn't very strong. It does have fibers in it, and if you could press those fibers into place in plastic with glue, between 2 pieces of plastic with glue, I think it's an interesting experiment. I might have a graph to show you of that. I was walking around Walmart one night, and I had the idea of something like mesh, and I thought, well, I'll buy some fishnet stockings. And it was a little embarrassing. However, I did buy the fishnet stockings and got home and realized, they're only fishnet when you put them on, and that's not going to work because you can't stretch them out. So I took the stockings back. I went to the fabric store and got if you received the materials for this lesson, you got some. I probably have some here, some net. And I was real excited with the net because like net fabric. So I don't know, you can see that. I thought that's going to be great. The results were, I thought, a little disappointing. However, I think it was a matter of adhesion and getting the glue to stick. So I also think on this particular slide, I have clay, ceramic, graphene, or graphite. And graphite is graphene in larger molecules, and graphene is really strong. It's the strongest material known. And I didn't try this, but I wonder about graphite, just the stuff that you would maybe put into a lock to lubricate it. Now, if it's a lubricant, it doesn't seem like it maybe would be very strong. However, if you can maybe just smear it into the rubber cement and make your sandwich, I think that's something I'd like to try. So the sky's the limit. Um, One of the things I tried was uh, household insulation, and there's what I got. And I didn't do the tensile test on this yet, but I don't think it looks very uniform. And probably the problem is um, getting pieces that are getting it to slough off. So I took a wire brush and just kind of started a wire brush, and that seemed to be a pretty good way to get the fibers to disengage. So I'll throw that out as an idea. But this is a great opportunity for kids to think about an idea, think about a design, defend their design, why they think it would work. And so that's why we included this lesson in this segment. So here's some data. So I think I might have told you in the notes, I kind of became partial to Film Guard, and this is what I've used all along. And I used to get it at Home Depot, and they don't have it anymore. I found it at Amazon, of all places. And I also tried the Husky, and I've got some other kinds here. So, I mean, I just bought rolls of this stuff and cut it up into reasonable sheets and give it to my students, and they can trim it to size to do their experiment. So these three graphs are on the left with no filler, just the plastic glued together. And I used rubber cement for this. Then I have two on the right, the fabric, the net fabric, and paintbrush bristles. I think paintbrush bristles are a pretty good option, because if you're thinking about modeling carbon nanotubes, the bristles are a cylinder, they're long, they're fibers, and it's a good model for carbon nanotubes. Certainly the scale is a zillion times too big. However, I think these results are interesting. Now, I did this on Excel, and if you do this on Excel, it will automatically scale the graphs for you, and they may all look the same. And the first time I did this, I thought, oh, I'm disappointed because the graphs, they don't show much difference. And then I realized that the scales were different. And so I went in and rescaled them all to from 0 to 50. And I'm sorry I didn't label these axes, but the stress was 0 to 50. And now it's a much more valid comparison, because without the filler, I see my elastic point is about at 10, and it is for the net fabric as well. The bristles don't really start to deviate much until about 15 or so. So there's a difference there. I couldn't get more than 20 newtons out of the plastic with no filler, and it just continued to stretch and stretch and stretch. Which brings up another point. There are two ways you can do this, and I would say try this 10 times yourself so you're comfortable with it and you can see what to expect. If you're pulling on the spring, you can pull 5 newtons, record that and let go. Bring it up to, if you're going in increments of 2, let's say 4 newtons, let go. 6 newtons, relax and let go. 8 newtons, relax and let go. The point in doing that is you can see that it goes back to the original shape. So it gives students a better idea of that elastic region. Then you're going to reach a point where it just kind of continues to stretch, and you can still do the same procedure, pull and let go and pull and let go, or you can just keep pulling. And if you just keep pulling and it keeps stretching, it's a little bit hard to record that data quickly enough. So I've resorted to maybe video recording it, which is one way to, if a student is video recording it and another student, so let me start over. A student's video recording and that student calls out, the newtons and the second student calls out the length, then that can be copied down at a later time and analyzed. So let's look at the net fabric. That certainly is a different looking curve. So what's happening there? It similar to the plastic with no filler. It doesn't. It holds its shape up until about maybe 5. So they're pretty similar. Now I've enlarged the graph on the left, obviously, so the points look further apart, but they were all taken at 2 Newton increments. But the fabric appears to just keep on holding. And I think that's interesting. It did not fail in the limit that we set. Here's something else. I'm disappointed because I don't see a failure in the fabric. And, I don't really see a failure in the plain plastic either. It continues to stretch. If you want to see a failure, then make your ribbon a little narrower. So instead of, a ribbon that's 4 centimeters wide, try making it 3 centimeters or 2 centimeters. If you get it too narrow, the spread of your filler won't be uniform enough, and I don't think it'll be very good. However, you could also, 2 options: make it a little thinner, less wide, or make it shorter, so that instead of starting with, I think in the experiment I indicated I would probably cut it to about 10 centimeters. Cut it to 7 centimeters and see what happens. And then you're going to have less material to stretch, and it may actually fail. So there are a lot of things you can do, a lot of parameters here, that the filler, the width, the length, that you can play around with. The bristles also is a uniquely different graph compared to the fabric. So which material would be, which of these 3 materials would I want to use for a space elevator ribbon, or in an application where I wanted a super strong ribbon? Probably none of them, because at least if I wanted to apply a force greater than 5 newtons, because they're going to continue to stretch. Now, the bristle material, I think, would be pretty good up to about 20 or 22 newtons. That's the elastic region where it might stretch a little, but it doesn't deform. But they all deform at somewhere around 25 to 30. But the bristle seems to be the most durable. Bill, anything? Okay.
Sorry, not right now, David.
All right, I'm going to stop sharing that for a minute. And in the last couple of minutes, I'm going to show you my Excel sheet. Now, I don't see myself anymore, but that's okay. Bill, can you see this Excel sheet?
No.
No, that's because, let me,
Yes.
okay. So here's my actual data, and these are the 3 that I just looked at. So in the materials, I provided you a draft of this spreadsheet, so you can feel free to use it. You will notice right here on the left, I have force in 2 places. I collected the data originally with, so I read off the force and I wrote in the length. So the column A and B were where I recorded my data. Then I calculated the strain, but I wanted to graph it so that I had the correct variable on the correct axis. And so I just copied the force into column F so that I can select those two columns and come up with the graph that I wanted. So that's why you might see force there twice. Let's see here. What else do we have? So there's a net filler. There's a net filler. That's all I have. In spreadsheet 2, I tried the spray adhesive. So the graph on the left, the data and graph on the left, are the Elmer's spray adhesive with no filler. The graph on the right is the same setup, except I added the Kleenex. I can't really make very good sense of this because, well, the sense I would make of it is that I have a better ultimate strength. Here's your ultimate strength up here at the top with the Kleenex, but there's a lot of stretch in here in between. Whereas with the plain plastic, I have a pretty good elastic region right here, up to about 20 or 22. Same thing we've had before. Now, these scales are not the same, so notice that. My point of deviation here is about 22, and here it's about 8. And I'm not sure why, because I just don't have an explanation. Let's see, was there anything? So what do we have here? This is comparing no filler. Okay, we've seen that before with bristles. It looks pretty similar actually. And the net. So there, I've lost track of the variables here because I'm just trying things to see what works. So my later trials, these are going to be more reliable. These are more systematic because I only changed one variable at a time. Okay.
Yeah, I just want to remind you of the time. It's 2:51.
Okay. I am going to break out here, and I think. Do we have any other questions? So before I let you go, let me say, if I like this, I'm kind of partial to this experiment because I've worked on it for a long, long time. If you're going to try it in your classroom, let me know. I'd be interested to know what you're going to do, how it works out. If there's anything I can provide for you in the way of resources to get things or how to do things. If you want to know what I did to make these boards or any components, shoot me an email. I'll be happy to a video conference with you and help you out. So, Bill, any closing comments?
I just want to leave a second. Does anybody have any questions before we wrap this session up? Thank you for the great session. Lots to think about.
Thank
This
you.
was great.
Here, I think you're the real heroes.
Hey, thank you so much. I'm excited to try this with my students.
Do it yourself multiple times first, because you may have some surprises.
Any thoughts on using biological substance like milkweed silk or such? Would it biodegrade?
I would love. That's a great idea. Milkweed silk. I would love to try that. I think that's a good idea. They don't have to necessarily be fibers per se. They could be granules. I mean, I think using something like, I bought clay, just like, powder clay. Some things may get messy, but you might be surprised at the results. The milkweed silk is a great idea.
Okay,